Hello and welcome to Controllers Tech. In the previous video, we looked at semaphores in FreeRTOS, both binary and counting. We saw how a binary semaphore can protect a shared resource by blocking any task that does not hold the token. We also ran into a problem called priority inversion, where a medium priority task was indirectly blocking a high priority task, not by holding the semaphore, but simply by occupying the CPU and preventing the task that held it from finishing. We left that problem unsolved intentionally, because the proper fix deserves its own video. And that is exactly what we are covering today, mutexes. A mutex works very similarly to a binary semaphore. It has a count of 1, and a task must acquire it before accessing a shared resource. But there is one key difference: ownership. With a binary semaphore, any task can release it, even if it was not the one that took it. A mutex does not allow that. Only the task that acquired the mutex can release it. This makes a mutex much safer for resource protection, because there is no risk of another task accidentally freeing a resource that is still in use. But the real reason we are here is priority inheritance, the feature that actually solves priority inversion. When a high priority task starts waiting for a mutex that a low priority task holds, the RTOS automatically raises the low priority task's priority to match the waiting task. This prevents any medium priority task from jumping in and starving the low priority task. The low priority task finishes quickly, releases the mutex, and the high priority task gets it without delay. We will use the exact same scenario from the previous video to demonstrate this. Same 3 tasks, same code structure, just with a mutex instead of a binary semaphore. So, let's start by opening the Cube IDE first. Here I have the project from the previous video. There are 3 tasks. The low priority task acquires the semaphore, and simulates resource usage by running an empty while loop for around 1 second. The medium priority task does not need the semaphore, so it can preempt the low priority task whenever it wants. It simply runs an empty while loop for around 5 seconds. On the other hand, the high priority task does need the semaphore to print its success message, so it has to wait to acquire the semaphore from the low priority task, while the low priority task is still holding it. Let's flash this project to the board so we can see the priority inversion problem that we covered in the last video. Alright, I'm going to step through to the main point here. This is the line where the low priority task actually runs. It acquires the semaphore and starts using the resource. The low priority task will use the resource for 1 second, but before that happens, the high priority task wakes up and tries to acquire the semaphore. However, the semaphore is already held by the low priority task, so the high priority task has to wait, which is expected behavior so far. But within that waiting period, the medium priority task wakes up, and since it does not need the semaphore, it simply preempts the low priority task and starts running its empty while loop. Now here's the real problem: after 1 second, the low priority task is ready to release the semaphore, but it cannot get the CPU back, because the medium priority task is still running its empty while loop for 5 seconds. So the high priority task has no choice but to wait for the medium priority task to finish first. This means the high priority task is being blocked by the medium priority task, not because the medium priority task holds the semaphore, but simply because it is starving the low priority task of CPU time. This is exactly what priority inversion is. The priorities of the high priority task and the medium priority task appear to be reversed. The high priority task is waiting while the medium priority task is running. To solve this issue of priority inversion, we use the mutex, which we will look at now. But first, let's rename our project to RTOS Part 5. Also, make sure you check the Update References box, so the renaming is applied at all the required places. Alright, the renaming is done. Next, we'll delete the debug configuration from the previous project, and also rename the IOC file to Part 5. Now open STM32 CubeMX and load the Part 5 project into it. We will keep things similar to Part 4, I'm not changing anything, so we still have 4 tasks with different priorities. We don't need the semaphores anymore, so let's go to the Semaphores tab and delete them. Now go to the Mutex tab. Here you can see there are 2 different types of mutexes available, one is the simple mutex, and the other is the recursive mutex. We will cover the recursive mutex later in the video, but first let's configure the simple mutex. Click Add to add the mutex, leave its name as mymutex01, and keep the allocation set to dynamic, so it takes memory from the RTOS heap. That's all the changes we need to make here. Now click Generate Code to generate the updated project. Now let's go back to Cube IDE. Here we can see in the main function, the mutex has been created using the function OS mutex new. Unlike a semaphore, where we had the option to make it either available or depleted by default, a mutex is always available by default with a count of 1, so any task that needs it, can simply call the acquire function to acquire it. We have our 4 tasks here, which we will now update. There is not much to change here. Instead of acquiring the semaphore, we will now call OS mutex acquire to acquire the mutex. The first parameter of this function is the mutex handle, and the second parameter is the timeout. The timeout works in the same way as it did for the semaphore. The function will wait for the mutex to become available. If we set the timeout to 0 and the mutex is not available, the function will immediately return with an error. Using OS wait forever is always a better option, because this way the task's execution will be blocked until the mutex becomes available. After acquiring the mutex, the low priority task will simulate resource usage by running an empty loop for around 1 second, and then it will call OS mutex release to release the acquired mutex. The medium priority task does not need the mutex, it will simply run its while loop without waiting for the mutex. The high priority task does need the mutex to print its success message, and after acquiring the mutex it will release it back. Now, we will also make use of the very high priority task. Here, we will print the priorities of all 3 tasks periodically. I'm using the function OS_thread_getPriority to fetch the current priority of each task. This task runs every 50 milliseconds, so we will be able to observe the priority changes in real time. Let's also change the printed text from semaphore to mutex in the task messages, otherwise it might cause confusion. That's all the changes we need to make. Let's flash this updated project to the board to see the output. Here you can see the processing starts with the very high priority task printing the priorities of all 3 tasks. The low priority task has a priority of 16, the medium task has 24, and the high task has 32. After the very high priority task finishes printing, the high task runs, acquires the mutex, prints its success message, releases the mutex, and goes back to sleep. This is exactly how it worked with the semaphore as well. After the high priority task goes to sleep, the medium task starts running. Since it does not need the mutex, it simply runs its empty while loop for around 5 seconds. Now I'll skip ahead to the part where priority inheritance actually comes into play. That happens when the low priority task finally gets CPU time. Here it is. Once the medium task finishes its loop and goes to sleep, the low priority task runs and acquires the mutex. After acquiring the mutex, the low task starts simulating resource usage by running its empty loop for 1 second. At this point, you can see the priorities are still the same, the low task has a priority of 16, while the medium task has a priority of 24. But as soon as the high priority task wakes up and tries to acquire the mutex, the priority of the low task suddenly rises to 32. This is exactly what mutexes are designed for, the priority of the task holding the mutex, which is the low priority task in this case, rises to match the highest priority among all tasks waiting for that mutex. So initially the low task had a priority of 16, but as soon as the high task started waiting for the mutex, the low task's priority was raised to match it. Now, when the medium priority task wakes up, it cannot preempt the low task anymore, because the low task now has a higher priority than the medium task. This prevents the medium priority task from interfering. After 1 second of resource usage, the low priority task finishes, releases the mutex, and the high priority task acquires it and continues its execution as usual. Note that after releasing the mutex, the priority is switched back to what it originally was. This priority boost is only temporary, and this mechanism is called priority inheritance, where the low priority task inherits the priority of the highest task waiting for the mutex. So we saw how using a mutex prevents priority inversion by implementing priority inheritance. Now that we've covered basic mutex usage, let's look at how recursive mutexes work. But before that, let's understand what recursive mutexes are, and why they are needed. Imagine a situation where a task acquires a mutex, and then somewhere deeper in its execution, it tries to acquire the same mutex again. With a simple mutex, this will cause a deadlock. The task is waiting for the mutex to be released, but the same task is the one holding it, so it will wait forever and never make progress. This is where the recursive mutex comes in. A recursive mutex can be acquired multiple times by the same task without causing a deadlock. The key difference is that a recursive mutex keeps account of how many times it has been acquired by the owning task. Every time the same task acquires it, the count increases, and every time the task releases it, the count decreases. The mutex is only truly released and made available to other tasks when the count reaches 0. So the rule with recursive mutexes is straightforward: for every acquire call, there must be a corresponding release call. If a task acquires the recursive mutex 3 times, it must also release it 3 times before another task can acquire it. A common scenario where this is useful is file handling. Imagine a task calls write function, which acquires a mutex to safely write to a file. Internally, the write function calls another function to allocate a block on the file system, which in turn calls one more function to update the file system metadata. Both of these functions also try to acquire the same mutex to protect the shared file system resource. With a simple mutex, this would immediately deadlock. This is because the allocate block function is waiting for the mutex to be released, but the write function is still holding it. With a recursive mutex, each nested call simply increments the count, and proceeds safely. As each function finishes and releases the mutex, the count decrements until it reaches 0, and only then does the mutex become available to other tasks. Alright, now that we understand what recursive mutexes are, let's go to CubeMX and add a recursive mutex to the project. Now click Generate Code to generate the project again. Here in the main function, you can see the recursive mutex is created using the same function os mutex new. Now I'm going to make some changes to the tasks. I don't need all the tasks running here, so I'm going to comment out everything except the low priority task. But make sure you leave the delay part, otherwise the very high priority task will keep running and never give CPU time to other tasks. Now we will add 2 functions to the project, function A and function B. Function A runs first, it acquires the mutex, and note that I am still using the handle of the simple mutex here. This is intentional. We will first demonstrate the problem that occurs when you try to use a normal mutex for recursive purposes, and then we will see how the recursive mutex solves it. So after acquiring the mutex, function A prints a success message and then calls function B. Function B will then try to acquire the same mutex again. If it succeeds, it will simulate some resource usage with a 100 millisecond delay, and then release the mutex. Control then returns back to function A, which releases the mutex it acquired, bringing the mutex count back to 0 and making it available to other tasks. Inside the low priority task, we simply call function A, which in turn calls function B. Let's also add a 5-second delay here, so the output doesn't repeat too frequently. Alright, let's build and flash this project to the board. Here on the serial console you can see that function A tries to lock the mutex and succeeds. But when function B tries to acquire the same mutex, it fails and there is nothing printed after that. What has happened here is a deadlock. The mutex is already held by the same task, and since a simple mutex has no awareness of which task is holding it, it simply blocks and waits forever. So we cannot acquire the same simple mutex again if it is already acquired by the same task. To solve this issue we have the recursive mutex. So now we will replace the simple mutex handle with the recursive mutex handle, and run the project again to see the difference. Now you can see that function A acquires the mutex, and then function B also successfully acquires the same mutex again. Finally, function B releases the mutex first, and then function A releases it. So we are able to acquire the same mutex multiple times, and you can do this as many times as needed, depending on how deeply nested your function calls are. This is exactly where recursive mutexes are useful. So to summarize this video, we saw how a mutex solves the priority inversion problem that we had with semaphores, by implementing priority inheritance. We also saw how recursive mutexes solve the deadlock problem that occurs when the same task tries to acquire a simple mutex more than once. In the next video we will cover task notifications, which is another way for tasks to communicate and synchronize with each other. It is similar to semaphores and mutexes, but more lightweight and efficient. That is all for this video. You can download the project from the article linked in the description of the video. Leave a comment if you have any doubts. Keep watching, and have a nice day ahead.